Okay, so I want to do number 4.2, number 13, because one, this is hella cool, and two, you can solve it without actually learning anything at all. It's really cool. You can get the answer in the back of the book thinking about this problem in completely the wrong way. So I'm going to show you how to think about this, and you're going to have to figure out why what I'm thinking about is totally the wrong way.
Okay,
Cool?
So you're telling us the wrong way to think about it?
No, I'm telling you a way that would work, but it turns out the thinking's a little flawed.
So we're supposed to think that way?
Yes, or no, think that way.
Both.
Got it.
Okay, so.
Expectation, Joe.
No, this is cool. This is a neat problem. So the problem says this. You have a room with an intake fan and an exhaust fan, right? In that room, you have some stuff that's giving off gas. Okay? Like you have some kind of chemical reaction going on in the corner because, you know, one of the grad students put two things in the same container that shouldn't have been in the same container. Right? So they're producing this kind of poisonous gas. And just to keep everything on track here, this room has a volume of V cubic feet. This thing is producing Q1 cubic feet per minute of gas. The gas is bad at C bar concentration. Cool.
Sure.
And it starts at C naught. Cool. Okay, and then this thing takes a second. The intake fan, so careful listening. Intake fans at one end of the laboratory pull in fresh air at a rate of Q2 cubic feet per minute. Right? Q2 cubic feet per minute. Everybody on board? Okay, and this is the sentence that gets weird. Exhaust fans at the other end exhaust a mixture of gas and air from the laboratory at the same rate.
So that could be the same rate as the first tube, or it could be equal rates of...
So I think it should be Q2 cubic feet per minute.
Or it could be equal parts.
Okay, and then you have to spend a second and think, because there's some room for debate here. And I just want to get by what I'm declaring the truth to be here. Okay? So it would be reasonable for you to wonder if the pressure in the room isn't going up.
Yeah.
Right? Because it seems like you've got Q2 feet per minute volume coming in from here, Q1 coming in from Magic Land, aka Chemistry Land, and Q2 also going out that way. That seems like there should be Q1 more cubic feet of air in the room, right?
Pressure.
Yeah, right. The room only has a certain volume, so the pressure should be going up, right?
Yeah.
Which should be making kind of weird stuff happen. Like, so let's assume, just for the sake of clarity, that Q1 cubic feet per minute is producing poison gas from something in the room, and it's consuming an equal volume.
So in other words, concentration
So
of gas is
isobar.
bad.
Yeah, in other words, concentration of volume is a thing.
Yeah, if the pressure increases, then the outflow.
You guys with me on that? Like, if we're going to make Q1 cubic feet of this stuff, we should consume Q1 cubic feet of other stuff in the room, so that the pressure in the room stays the same.
So we're assuming both constant volume and constant.
Yeah, yeah. I'm assuming
So
that this
is the
is
temperature going
eating
up?
something.
Okay.
I have no idea or care.
Okay.
Cool? You guys good with this assumption? This is just an assumption. All I'm doing is assuming that the volume of the room isn't doing something weird. Cool? All right, so what I should try to do is write a differential equation to model what? What's the cardinal rule of compartments? They're, don't model concentrations. That would be dumb.
The amount of poison gas in the water.
And the thing you want to model is the amount of poison gas in the room. Right? I mean, it should be the amount of stuff, right? In this case, we're talking about poison gas, so we should be talking about the amount of poison gas. So we're going to let, I don't know, what do you want? Letter, poison gas?
P.
Oh,
P. So we're going to let P of T be the amount of poison gas in the room.
This is different than the last one because we were doing mass and this is.
Yeah, this is
volume.
weird. Right? So the weird is that I should be trying to figure out how to write my differential equation. And so first I'm not modeling a concentration, I'm modeling the amount of gas. Then I need to remember the other cardinal rule of compartments, which is, what's your differential equation consist of?
rate inflow out.
Yeah, the rate of increase of stuff is the flow in minus the flow out, right? So dP dt should be, here there should be poison gas in, and here we should be subtracting, and there should be poison gas out, right? And each of these should be made of two things. Let me do poison gas out just for comparison purposes, because I think that one will be pretty easy. And let me maybe move my minus sign. Okay, so I think these are always made out of two things. What are they made out of?
Concentration times the flow rate.
Yeah, they're a concentration times a flow. They're always a concentration times a flow. They're never anything else. So, what is the flow leaving the room? Q2. Cool. What is the concentration of gas in the room?
C.
So at the beginning it's C naught, right? And the deadly level at C bar. But what is it right now?
Is it C divided by the volume? C over
No.
Close.
How much poison gas is there?
P of T.
Yeah, there's P poison gas, right?
Oh,
How much volume is that P poison gas spread out through? V. So it's P divided by V. Poison gas spread through V volume. Cool. At this point, it would make sense for me to spend just a minute worrying about units. So, what are my units? Q2 is a cubic feet per minute, right? Volume's in cubic feet, and P is in, yeah, it's the amount of poison gas. How am I measuring poison gas?
well, it's coming in a volume per cubic feet, so it's.
Yeah, it's coming in at a volume per minute, right? So the total amount's going to be a volume. Okay, and this is where things are weird, right? Because what I have here is not feet cubed over feet cubed, it's feet cubed of gas per feet cubed of air. And the flow out is feet cubed of air.
Well,
Like air poison mix,
Oh,
right?
That's right.
yeah,
because it
hold
really-
on. Wouldn't that volume be a volume of poison gas plus air?
Yeah, so what if I just called it mix,
Yeah.
right? So the flow rate out is taking mix out of the room, and that mix has some poison gas split per mixed air in the room.
Yeah.
Right, in the worst possible case, the amount of poison gas in the room would be all of the volume. right? And this quantity would be 1, right? The lowest it could ever be is there's 0 gas in the room, and it's all air, right? The air mixed with 0 poison. Guys with me on this? So if I do this cancellation here, right, for my units, I get feet cubed of gas per minute. You guys with me? Okay, now I have to model the other 2 sources. So the intakes, I claim there's 2 intakes. One of them is really easy.
Q2,
Yeah, Q2 is super easy.
but it's times 0.
Because how much poison gas are you getting from Q2? 0. So there's Q2 times 0. Right? That's that fresh air intake. Pretty good. Okay. Now the other one
Q1.
is Q1. I need some units on this one. What are the units on Q1?
Cubic feet per minute.
Feet cubed per minute. Okay, now
Times T.
doesn't depend on time. This is the weird thing. What's the concentration of poison gas being generated down here?
It's just 1, right?
Yeah, all that stuff is poison gas, right? That's 1 cubic feet of gas. Oh, oops, sorry, I switched colors. That's 1 cubic foot of gas per cubic foot of mix. And the flow rate is again a mix, right? But all of it's poison gas. We just talked about what would happen over here if P and V were 1, right? If P over V were 1. That's what's going on at the source, right? It's just 1. You guys cool with this? So the mix is canceling. Again, that's cubic feet of gas per minute. So all told here without units, I have that dP dt is Q1 minus P over V Q2.
Why is it not T component on loss there?
What's that?
Why does it not depend on T? It seems like what is should be a function of T. Why is it not there?
Oh, because this flow rate's always constant, right? The amount of poison gas in the room basically has 2 components, right? Like the rate at which the amount is changing is it's going up by the stuff that's being created and it's going down by the stuff that's being exhausted. That doesn't depend on the time except in that the amount of poison gas in the room changes over time. Everything else here is constant. Right? It's being created at a constant rate so that the increase in poison gas in the room is always the same. It's always just the rate at which it's being created. And then the exhaust changes because at first, when there's not very much poison gas, right, the exhaust isn't getting rid of very much. But after there gets to be a lot of poison gas, then the exhaust is getting rid of a lot of poison gas. You guys see this? Okay. Now, for the cool trick. They want for you to figure out a Q2. So I never did tell you the punchline of this question. The question is asking, what do you set Q2 to be so that the exhaust always takes care of your gas and keeps it below C bar concentration? In other words, what do you set this fan at to make it so this is never dangerous?
Is it
What is
Q1?
it? What's the lowest you can set it at?
Yeah, what's the lowest speed you can set the fan at, right?
Q1. Is it Q1? Because then you have like a cooling type looking situation with the Q1 times 1 minus P over V.
Remember that's both of these, right? right? So what I need to find the maximum concentration, right? Okay. So talk me through how you would find the maximum concentration.
So you have to find out a formula for the amount of poison gas in that fluid.
Okay. So you'd solve this for P, right?
Yeah.
You guys all with that? So you get some P of T, right? We good?
Wait, so
Duh.
it is a P of T then? It becomes a function of time?
Oh, P is always a function of T.
Oh, okay.
P is the amount of poison gas over time, right? And what you want to find is what's the highest the concentration ever gets, right?
Uh-huh.
Well, it seems
But the
like-
volume is always the same, so the concentration may as well be the amount. So you want to find the maximum of this P of T function.
Okay,
Is Q1, 2, and
Right.
V all constants?
Yeah, they're all constant. So
yeah.
could you solve this?
Yeah, I think I have an idea. So you want your concentration of poison gas to max out at, a certain level.
Yep.
So when it's maxed out, the concentration isn't changing, right?
Or it'll
So
approach
dP over
asymptotic.
dt would be 0 when it's maxed out.
Yeah, because when you want to maximize a function, right? You take the derivative, you set it equal to 0.
Yeah, so you can plug
Right?
0 for dP.
Whoa, 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 hang on.
Okay.
I just want to go through the thought you could have is go find P of T, right? And then differentiate with respect to T,
Mhm.
and then set that equal to 0 and solve for T, right? Why?
Okay.
Just plug 0 in for P of T right here, or dP dt. So, if we do that, right, plug 0 in, we get Q1 minus P over V Q2.
Yeah.
So it's VP, and then VQ.
And then solve for, what am I interested in?
Q2.
Q2, right? Oh no, I'm not. Because I'm interested in when does the maximum occur?
I thought you
Oh,
wanted
what-
the minimal.
Yeah,
value.
what's the question asking?
So-
exactly?
The question is asking, what do you set Q2 at to keep P of T divided by V, right, the concentration of gas, below C bar?
Yeah, so take that equation and just plug C bar into it
For where?
for P. Yeah, you'll need
Okay, so you're saying like,
Glad you got like the new all.
okay,
yeah.
Because C bar is like, it's pretty much the same.
so you got 0 is Q1 minus C bar over Q2V.
And
No, no.
Oh.
then- Oh, wait, you,
Sorry, I just mismatched symbol.
Times Q2.
So 0 is Q1 minus C bar over V Q2.
And it's all
Wait.
C.
is
Isn't
bar
C
is
C
is
the
the
concentration
concentration
itself,
or
right?
the,
C bar is a concentration. So what do I need here? Instead of P of T, I need the amount, right, of gas that you would have at the C bar concentration. So what did I say over here about keeping P of T smaller than C bar?
yeah,
Well, I said P of T over V has to be smaller than C
So we're
bar.
gonna go for V squared?
So P of T has to be smaller than C bar over, or C bar times V.
yeah,
You guys with that?
yeah.
Yeah, and then the V's cancel.
Okay.
So you get 0 is Q1 minus C bar Q2. So then solve for Q2, right?
Well,
That's that.
Would that be a flow rate still?
I don't know. Let's think about it.
We have a flow.
So Q1 is a flow rate, right? So that's a feet cubed per minute. What's C bar?
it's just concentration.
Your lethal,
VQ.
your whatever, undesired
Per-
concentration.
It's
V cubed of y is inverse V cubed of V.
Oh,
Yeah.
It's in feet cubed per feet cubed,
That's fine.
right?
You can gas over
So this thing's unitless, right?
wow, that's weird.
And so you still have a flow rate. That's cool. That's different than what I was going to do. What I was going to do is say, okay, so if I figure out when that maximum occurs, right? So if I solve this for t, right, to figure out at what time the maximum occurs, I'll get that is at minus, so let's see, I subtract q1, and I get minus p of t over v q2. Flip the signs on both sides, fiddle this about a little bit. We get q1
V over Q2.
q1 v over q2 is p of t, right? So you take p inverse of both sides, just assume it's invertible. A little weird. And then take that and trot it up into here and solve for q2, and you get exactly the same thing.
And we can do that if we actually solve for P.
Yeah, you could do this if you actually solve for p, but the kick is you don't have to,
Maybe we got it.
right? It turns out, yeah, this is the way you do it. You get to this. Like, check, done, cool. So,
Wouldn't it approach that asymptotically?
yeah, that's actually the good question, is like, how do you know it assumes the maximum in finite time?
Because like, how can we get it? We'll never have a derivative of 0. So
Yeah, the derivative approaches 0 asymptotically, probably. It turns out that if you actually solve for p here, and then take the limit as p tends to infinity, or as t tends to infinity, and then set that smaller than c bar times v, you'll get this exact same thing. This is just really cool because we never actually had to solve this differential equation, right? We just wrote down the differential equation and thought about it a little bit. Cool?